Hey there. So today's lesson is from Physics Chapter 5. It's lecture number 2. We are going to be covering On Your Own Problems 5.8 to 5.12. We're going to finish out the chapter. And the first problem we're going to work is on page 165. And we're on page 3 of your lecture notes. So a little bit of vocab to start. So kinetic friction is the frictional force applied while an object is in motion. Okay, so if you were sliding something across the floor, it's resisting you, and that frictional resistance we call kinetic friction. Static friction is the frictional force that applies to initial motion. All right, it is the force it takes to break something loose. So you've probably noticed that if you're pushing a heavy box along the floor, it's harder to get it moving than it is to keep it moving. All right. So the object will move when a force greater than the static frictional force is applied. So in order to get something to move, you have to overcome static friction first. All right. And static friction is always greater than kinetic friction. So we've got our frictional force equation that you've got to memorize. So let's put an asterisk beside it. Little f is equal to what we call the coefficient of friction. That's the Greek symbol mu times the normal force. All right, so frictional force is little f. Mu is the coefficient of friction, and we talked about the normal force on the last video. All right, the normal force in chapter 5, since we're not on any angles, is just the weight. Now, you can have two different kinds of coefficients of friction. What we call mu sub s is the static coefficient of friction. Okay, so, and then mu sub k is the kinetic coefficient of friction. Mu sub s is always greater than mu sub k because, again, it takes more force to break something loose than to keep it moving. Okay, let's use these concepts in a few problems here. So first of all, 5.8 says a man is pushing on a 12-slug rock. What is the maximum frictional force that will keep the rock from moving? Okay, so we're just trying to get static friction here. All right, so friction is just going to be mu sub s times the normal force. Okay, we know that the normal force is just equal to the weight. Weight is mass times gravity. We know that this is a 12-slug rock. Remember, slug is mass in the English units. Gravity would be 32. So the weight is 249.6 pounds. So our frictional force is equal to the static coefficient of friction, which in this case from the book, 0.65, just from the problem, times 249.6 pounds. All right, excuse me, I'm so sorry. That's 384 pounds. So you have to do a little bit of erasing here. So I looked at the wrong number on my sheet. So it's 0.65 times 384 pounds. And that is 249.6 pounds. So sorry that I made you erase a little bit there. Just pause the video a moment so you can clean up your notes. All right, let's look at 5.9. So 5.9 says a student starts to push a 22 kilogram pile of books across a desk. If the pile of books is at rest, what frictional force must be overcome to get the books moving? And we have both the static and kinetic coefficient of friction. Well, we don't even need the kinetic coefficient of friction. We're just trying to get the books moving. Right? So this problem is really exactly like 5.8, except we're in the metric system here. We know that our frictional force is going to be mu sub s times the normal force. The normal force is equal to the weight. That's mass times gravity. Our pile of books is 22 kilograms. Gravity would be 9.8 meters per second squared. So 22 times 9.8 is 215.6. What's the unit on that? Do you remember from last lecture? Not pounds, but newtons. So now we can get the frictional force. 0.45 is our static coefficient of friction. 215.6 newtons on the normal force. And so you've got to overcome 97 newtons to get this pile of books to start moving. All right. So this is a slicker surface, so it doesn't take, it takes less than half the weight just to get it moving. That wasn't the case in 5.8, which was, it had a higher coefficient of static friction, wasn't quite as slick as in problem 5.9. All right, let's move on to 5.10. So in 5.10 and 5.11, we're going to draw a free body diagram. We talked about that. It's also mentioned in the video I had you watch. So this is just on the next page, page 166. That problem reads, a man pushes a 6,675 Newton rock with a force of 95 newtons. If the rock is already moving, what will its acceleration be? Well, how is this different from the last problem? Well, it's already moving. So it's a kinetic situation. We're going to use mu sub k instead of mu sub s. All right, so here we have, let's go ahead and draw a free body diagram. So we've got the ground, this rock with a surprisingly flat bottom. The man is pushing with a force of 95 newtons. We know that friction at the surface of contact is opposing us. We're going to go ahead and calculate that in a minute. So we'll call that F. We know we have the weight of the block going down. That's 6,675 newtons. Right? We don't know the mass of the rock, but we can figure it out. And then the normal force. So that's a force diagram. All right, which and also called a free body diagram. Well, we're going to use Newton's second law. The summation of all the forces is equal to mass times acceleration. We're going to solve for acceleration. Well, if we consider the positive direction to the right, then the sum of all the forces, we would have big F, which is 95 newtons, minus little f, which is the force of friction, is equal to the mass times the acceleration. So we know big F. We can calculate the mass and the force of friction, so then we can get acceleration. Okay, the force of friction is going to be mu sub k times the normal force. Right? The normal force, of course, is just the weight. So that's 0.011, which is a crazy slick surface. No one could walk on that. It's almost basically no friction. And the author made it so small because he put too small a force for such a heavy rock there. Times 6,675 newtons. So our force of friction is 73.4 newtons. Now, if you go through the calculation and the force of friction was greater than 95, then the rock wouldn't move. But since the force to the right is greater than the frictional force, which is opposing the motion, then the rock will go ahead and move. Okay, we also need to get mass. We know that mass is weight divided by gravity. The weight is 6,675 newtons. Gravity would be 9.8 meters per second squared. Right? And that mass is 681.1 kilograms. Very heavy rock. So now we can use this equation. Our force to the right, what the man is pushing at, 95 newtons, minus the frictional force, 73.4 newtons, is equal to the mass, 681.1 kilograms, times acceleration. So acceleration is going to be 95 minus 73.4. Right, it's 21.6, right? Divided by, and you could have gone ahead and done that in your calculator, 681.1 kilograms. And so that acceleration is 0.032 meters per second squared. All right, so not a very, very big number because it's such a heavy rock and the man wasn't pushing it with very much force. All right, pause the video if you need to, and we will hit number 11 on your own 5.11. Okay, so 5.11 right underneath on page 166. That one says a child pushes a 2.3 kilogram toy along the floor at a constant velocity. That's really important, constant velocity. What force is the child exerting? Okay, one thing I want you to ask yourself real quick. If you have a constant velocity, do you have any acceleration? Think about that. So what force is the child exerting? Well, let's draw a free body diagram. So on your test, I want you to draw free body diagrams where they are called for. So we have a toy. I'm just going to draw a box and label it toy. I realize it's not what it looks like. So the child is exerting a force. We don't know how much, but I'm going to call that big F. We know that we have a frictional force opposing the motion. The toy is 2.3 kilograms. So we have weight and normal force. Normal force is just going to equal the weight. So weight is mass times gravity. So that's 2.3 kilograms times 9.8 meters per second squared. All right, so 2.3, so it's going to be, what, a little under 23, right? That is 22.54 newtons. All right, so our normal force is also 22.54 newtons. Okay, let's get the force of friction. Force of friction, so the toy's already moving, so it's mu sub k times the normal force. Mu sub k in this case is very small, 0.13. Just, you know, your average road, asphalt road, has a mu of 1. So you can see this is much slicker than that. So the author used numbers that were a little bit on the small side here. Times 22.54. So that frictional force is 2.93 newtons. So we have the sum of all the forces is equal to mass times acceleration. The sum of the forces would be big F minus little f equals mass times acceleration. So we've got one going to the right, one going to the left. However, constant velocity means there's no acceleration. So Mass times acceleration would be 0 since acceleration is equal to 0. So 0 since we have a constant velocity. So I have big F minus little f is equal to 0. So big F is just equal to F, which we figured out a little bit. 2.93 newtons. So a pretty cool problem there. If you're moving at a constant velocity, that makes the math quite a bit easier. All right, let's finish this chapter up with 5.12. All right, 5.12 says a tennis ball hits a tennis racket. What two forces besides gravity exist in this situation? What are the visible ramifications of these two forces? Well, the author wanted to have one on your own problem that talked about Newton's third law. So this isn't a math problem. So a good way to answer this would be every action has an equal and opposite reaction. All right, so the racket exerts a force on the ball, and then the ball exerts an equal and opposite force on the racket. Right? And you would feel that if you were the one playing tennis or pickleball here or whatever the heck that is. You would feel that in your arm, right? The ramifications of that force. Okay, so we finished chapter 5, a very short chapter. Chapter 5 goes along with chapter 6. So the homework, we're going to do review questions on page 174. We can finish those up, do 9 and 10. And then the practice problems on page 175, finish those up. You can do 7 through 10. All right, so that does it for chapter 5. I will see you on the chapter 6, lecture 1 video.